have two types of sub branches from VLSI side. Those are front end and back end. Maybe you all must have heard about the front end and back end designs, even in the software designers, software development side, or web developments also. Same as it is, we also have two types of sub branches from the VLSI also, and one will be the front end and one another will be the back end. So front end, what a front end developers do is the department's called analog layout RTL designers. So actually in front end we will be having a analog layout designers who actually designs analog systems. So we all know, right? We all will be knowing the analog components such as amplifiers, rectifiers, amplifiers, all analog components which are designed by analog designers. And we'll be having a department called RTL designers. Have you all heard about RTL? A registered transfer logic, a Verilog code, or a VHDL, or a system Verilog code. It's like a same like a binary. We are converting some of our actual language to a binary, just like a C and Python programming languages. We are writing it in a Verilog. It's a separate language called register to register transfer level logic. So that will be the another department which is also a front end one. So what we do, I'll give you a just overview about all these front end departments. I'll go very deep into it, deep into the physical design, as you can see on my screen. So Verilog. So what they actually do? So RTL designers will get a inputs from a circuit design. As you can see here, a circuit designers. So circuit designers, what they do is we will be having a client in our actual VLSI industry. Please listen it carefully. I'll tell you what actually the industry, how an actually VLSI industry runs. This will be not seen by us till now. So there will be two types of companies. Everyone knows it. One will be the service based, and one will be the product based. So if someone need a project or someone need to develop a chipset, for example, we all uses sorry, we all uses a laptop, right? We'll be having a i5 processor or an AMD, a Ryzen, or generally we use a Intel Core i5, Intel Core i3 process. Generally, we use in our laptops. Assume an Intel Core i5 or an i3 is a new project which is taking over by Intel now. So some client will come to the Intel and say there like we need a high fastest chipset, advanced chipset from you, which need to be in a very fastest manner. Example, if their oldest chipset i3 is clocked at 3.3 gigahertz speed, now an advanced i5 chipset must be clocked at 4.5 or beyond that. So they will be getting a set of rules and everything that will be known in the actual classes, actual our courses from Waspire. From that set of rules, these Intel will start making process which the work will be divided in the departmental wise. So for that designs, the circuit designers will design a schematics which is using CMOS MOSFETs or gate level. You take it as a gate level. So everyone knows gates, right? We all know gates. You can, yeah, yeah, you can. So circuit designers, a basic circuit designers will design every circuits with a gates. For example, if we want a 8 by 1 multiplexer using two half adders, the circuit designer will design a circuit using a appropriate gates which having specific specifications which have set by the client. So there will be a circuit design ready from the circuit designers. Then that circuit design will be transferred to the RTL designers. Till now, the circuit design is a paperwork or a electronic paperwork. Then that circuit is sent to a second department which is called the RTL department. Okay. So RTL designers, what they actually does is they will transform that circuit as it is to a Verilog code. They transfer that logics and every circuit to a Verilog code. Transfer to a Verilog code. The code will be ready. If we simulate that code, if we simulate that Verilog or RTL or VHDL or Verilog code, we will get our desired output. For example, we'll take a small example, and for your kind information and note, we are mainly focusing on physical design. We are only mainly focusing on our physical design. I'm saying you what actually does from a scratch to actual processor outcome. So please listen. So in that very law code, if we simulate that, assume we are taking a project called a calculator chipset for a calculator, processor for a calculator. So the very circuit designers are designed a circuit which will act as a it which can having a capabilities of doing a multiplications and many mathematical works. Fine, well and good. Then that will be transferred to the register transfer logic, which will be a Verilog code. If we simulate that, if we give a 5 plus 1 in our input, the answer will be the 6. Job done. It's just a code, but there is no any processor built till now. Our everything logic is ready, code is ready. Till now, the actual physical chipset is not yet designed. So here we are the responsible persons to design the actual chipset, physical chipset, using the inputs as a RTL or a Verilog code, and we'll be having some design rule constraints, a set of rules to design, which will be managing our application department after design and taking inputs from our RTL designers. And very important key point, RTL designers are only bothered about the logic function itself. Just a logic function. They are not bothered about any timing constraints. For example, if we are doing some math calculations, so let's take a same example from the past. If we are doing an addition calculation of a 5 plus 1 and we have typed an equal to, they are only bothered about the answer 6. But as a physical designers, static timing analysis engineers, we also bothered about the timing, like the answer should be displayed in a split second. Answer should be 6 and that should be displayed in a split second. Let's take an example. You have using a calculator, you have typed the 5 plus 1, same example. You have pressed an equal to button. You are getting the answer 6 displayed after 5 minutes. Is there any use? No, right? There will be any no use. So as a physical designers, we do bother about timing constraints. We do bother about we are bothering and we are designing the actual chipset. Here, the different departments from the physical design are different stages of the physical design. After physical design, there will be the verification, physical verification and sign off team. Then there will be the fabrication. It's the last one, like packaging the chipset, packaging the designed one, and actual chipset will be out from the some factory. Okay, we will be having some of some flow to follow from physical designing. First step, we'll be doing partitioning. Second, we'll be doing a floor plan. Third step, we'll be doing a power planning. Fourth, we'll be having a placement. And after that, we'll be doing a clock tree synthesis. And after that, we're going to do a routing and timing closure. Okay. Before going to explain all this, just look this, just keep it in our mind. These are the order. This is the order we are going to learn and practically implementing in our tools. Let us close this for a while. So till now, we have learned or we have completed something about something from introduction to the industrial VLSI, how the companies work, different set of departments from VLSI, and our actual VLSI physical design things. So now we'll go to the fabrication steps. So all know about fabrication, right? It's a basic things which engineering colleges does. So it will be very basic. MOSFETs. MOSFETs itself. MOSFETs itself, we call it as a gates. Gates. And afterwards, when we are going to the actual course in Wayspire or anywhere else or whatever it may be, when we are doing an actual industrial training, we will be calling them as a, not as a MOSFETs or a semiconductors or gates. We will be calling them as a standard cells. Standard cells. Standard cells, okay. How a N-channel MOSFET is built and how P-channel MOSFET is built, right? And how a CMOS, so the complementary MOSFET is built, and you know the steps and things already, right? If you all know this, I will show you the another semiconductor we are actually using in an industrial. Maybe someone knows and someone not, someone don't. So what actually we uses in an industry? You can type like, do we use a semiconductor as a MOSFET or we have an any other advanced one? Okay, so as per engineering colleges are all, we are just using a CMOS, complementary MOSFET, right? Yeah, we are using a CMOS. Every colleges and everything we have learned, we are just using a CMOS. But in actual industry, we are not using any CMOS. We have upgraded it to the FinFET. We are not using any MOSFET. We are using a FinFET. So FinFETs are the advanced version of MOSFET, which will be very similar to the MOSFET. Very similar. Let me search in Google. You can see this. This is a general planar MOSFET, and this is a FinFET. We will be having a fin, like you guys all know about shark fin antennas, shark fins. You know, right? The shark contains a fin at top of it. Exactly like that, we will be having a fin in a FinFET. It is a MOSFET, but we'll be having a extended fins that are source and drain. The actual source and drains are very much grounded to the base layer for the MOSFET. In a real time, we'll be having a fin. As we are using, by using a FinFET, we can access the source and drain in a very faster manner without and we can minimize some complications when we are doing some routings. Okay, so we are using some FinFETs. Right. Right. FinFETs are not more faster than MOSFETs, but FinFETs are more accurate than MOSFETs and more easy to access than a MOSFETs. Sorry, getting everyone. And I don't want to waste our workshop time discussing about the these fabrication steps again. Physical design, some of the contains. This is my personal PPTs, which everyone follows when we are using some type of tools. So everyone we use some set of tools to design our circuit or PCB or a processor, right? Those are called CAD tools or EDA tools. Right? EDA tools, mental graphics. So generally, I'm going to explain you the first. I'm going to explain you the types of tools we are using, and I'll explain what are the difference between the tools. Fine, you'll get a clear picture of it. Just keep an eyes on the screen, guys. We'll be having a different types of tools, and we have a big two players in our VLSI industry. Fine. Till our engineering graduation, colleges like general internal colleges or tier 3 colleges only shows us or gives us an access in the tools called Mentor Graphics, T Spice, and Mentor Graphics and T Spices. Right? Have we gone through it? Maybe everyone gone through it. So we have some two big players called Cadence Designing System. This is the first one. Like the two are in the same level of things. Synopsis. So we are having a two big players which we are going to use in our industries. Every industrial company, even it is a product base or even it is a service base, we are going to use these two tools to design our complete IC or integrated circuit. Okay, the mentor graphics will be the third one, which will be not more complicated to as these two. So here, and I was expert in a synopsis tool. I, as a VLSI engineer, I am the expert in synopsis tool. So in Vspire, we are providing the synopsis tool. Like generally, the technological notes, right? We'll be having a technological notes when we are going to design any circuits or any chipset. You all heard about build technology. You have heard, right? Like when you are seeing some ads or in the mobile phone processor ads, 5 nanometer build technology, 9 nanometer build technology, 6 nanometer build technology. Have you heard it? You have heard. So actually, when we are going to learn something in some institutions over offline, online, everywhere, government will only give a permissions to the educational based purpose till 45 nanometer build technology. That's it. We'll get only the 45 nanometer build technology. But here in Vspire, we are providing a 28 nanometer build technology synopsis tool. We gonna build a two we going when we are going down, like when the nanometer build technology, the technological node going downside. For example, exactly what is mean by nanometer means the size or thickness of a gate in a MOSFET. When it is going very thin, the complication of the designing inside circuit will become more complicated, right? When the chipset goes more thinner, We need to place millions of transistors in the same packed area. Will be more complicated, right? So here we'll be designing in our 28 nanometer build technology, which was Synopsys. Synopsys here further divided into two types of tools for two segments of the project. When we are doing a physical design, we will bother, as I said, we will bother about timing constraints. We also bothered about our physical design. We will construct the processor. Just like, for easy way, I can say, when we construct a building, we'll have, right, we have some process, right? We will design a plan first. We will start working. We'll dig holes and we'll place some basement. We'll partition the rooms, floor planning, power planning, everything we does, right. When we are constructing some buildings, in the same way, our chip architecture will be in the same manner. When we want to understand in a more clear way, in an easy way, we will do it in the same manner. Right, getting. So as we are bothered about the static timing analysis, okay, like timing of a chipset or a logic, we does a static timing analysis in our tools. Okay, we does a static timing analysis in our tools. Then after, we will design for static timing analysis purpose, we use a tool name called design compiler or a DC compiler, design compiler, which was sponsored or which was in the Synopsys tool itself. Second one, when we are going to design a chipset architecture, we gonna use a tool called ICC2 shell. ICC2 shell. Right. And we also offer a bonus course in our VLSI PD program. We are going to, operating systems. We only use a Linux operating system for our tools running purpose. Why? As Linux is not a graphics oriented OS. As Windows, we can see there will be a lot of graphics. But in Linux, we use only commands to do everything. We only use commands. Bash, shell, tcsh, tcl scripting. You may be knowing in the further classes if you wanna take a or something. So we'll be doing, basically we are doing two types of works in our PD or as a physical designers. We are going to do a static timing analysis and synthesis, synthesis and physical design. So we will be having our tool. We'll be having our tool in a server house. We will be maintaining a server house, which was installing all Synopsys softwares. In a Linux commands, we'll be having a server house. From there, we will be accessing that server in a particular separate IP address to our laptops. Okay, and Synopsys tool access will be very costly if we don't go through the institutes. If we want our own itself an access, but 28 nanometer build technology single access will be costs around 50 lakhs per year. It's too huge. So, and they don't give any permissions to access also if there is no industrial expert to maintain the server. So here we have a server house, which was Synopsys tool. We will be getting a server access. We will be accessing it from a VNC's IP address. So please keep your eye on the screen. See here, this is my VNC screen. I'll be having an account through my name, and I have a particular IP address to access my server access. Please everyone, just be responsive. Here itself our actual workshop starts and we gonna learn something what actual industry does. So this will be these will be the server access. These will be the server window, which will this window is a separate computer itself here. We are accessing the server system from our personal computer. We are accessing that display from our server from our personal computer. Okay, so this is a server's window, a server's Windows desktop, and this is running in a Linux operating system, Linux OS, and which is running on CentOS, Linux CentOS 7, which is an advanced version. All right. So, as it is, I have said already, as it is a Linux operating system, we don't have any graphical interface. We'll be having minimal graphical interface. If we want to access some files, we can't just go to these things and go to the files. But for that, everything we need to go to the console. So everyone knows console, right? Our Windows has a command prompt. We do some commands when our system get hang, or if we got some data loss, or if it's anything, we do some commands to back up, or if our computer gets hang, or we just forgot some passwords, we just go to the command prompt and we does something, right? In the same way, in the same way, we can access files as a graphical interface in our Windows. In the same way, in the Linux, we are going to write commands to access files. Okay, this is the path we are currently located. Assume, please guys, everyone listen. Assume using a Linux operating system is just like a playing like a game, Pokemon Go. Have you heard about it? You know, right? So we are at one place in the road map. We are at the one place, and that address is this one. That address. We'll be knowing our current address by PWD. See, this is our current address. In this place, we are standing. So if we want to go some other files, we need to see first whatever the files we have in the pathway. So we'll be having this many of files. We can see this many of files, right? So if we want to go to some files, all right. So if we want to go to some of the files, we want to type some commands. We'll be having some more and more commands. Okay, just leave it. It will be shown said. It will be the another subject called a bash or Linux command. So we'll be evoking our tool here. All right, we will be evoking our tool here. So how to evoke a tool in a Linux? In a console. So we have discussed, right, what was the name of our tool to design a physical design, to have a construction of physical design. We have learned it as a ICC2 in synopsis, right? Just wait. Let me clear all this and start again. See, it takes one moment and the tool will get evoked. So everyone, you can see till here it is a Linux console system shell, and after this we are evoking the ICC2 IC compiler 2 synopsis tool. Right? You can read this. You can read this. This is a ICC2 shell. Okay. From here, everything we gonna do is using all. We will be doing everything with the commands. Physical design will be done completely done using a commands only, commands itself. So I gonna show you the past projects of our students, past projects of our VLSI students, or explanation to them by us. I'm gonna show you them. We don't have any all the time to do complete project now, so we are going to show you the past projects of them. I'll show everything here. So actually you will get a idea, or you will get something that what actually the industry does. All right. So in industry, till here will be done, and you will be getting some set of rules. You'll be getting RTL code there as an input to you. You'll be getting some constraint, design rule constraints, timing constraints, and etc. Example: when you are going to construct a building or an apartment, you'll get a plan first, right? You'll get a plan. You'll get a bricks which have set of rules like a brick size, right? Brick size, how much? Example, brick size will, as a client, as client you are the owner of the building, so you have said to the constructor that you need to construct my building using 6 is to 3 ratio bricks only. You have said to them, so you'll use that, right? We will be acquiring all the inputs when we are starting construction of building. As the same way, we'll start acquiring every files, technological files, library files. We'll be creating a library to access every tools and things from there, and we'll start constructing. Okay, and we start creating library, and we start constructing our chip architecture. So we have opened our library, which was already done. There will be the another commands to create a library. Okay, we have opened. In that library, we'll be having a several blockages, like day one work assigned. That will be done in a one block. Maybe you can't understand anything by seeing everything directly. It will be a long procedure. It will be a long procedure. When we join to some courses, we can do that, or we can learn it step by step. So opening block, right? We are going to open blocks. See here, we have several blocks here: floor plan, boundary, complete CTS, and whatever it may be. You don't know this. These everything. You can read this right up before floor plan, CTS, clock tree synthesis. CTS means a clock tree synthesis, placement, route, tie. These all are the process in a feeding. Example, like you can see here, right? Partitioning, floor planning, power planning, placement, clock tree synthesis, which is CTS, routing and timing closure. In the same way, we are going to construct our project in an easy manner. Like we are going to design our chipset. So we'll open very first thing. Partitioning will be done in a not done in a graphical interface. That will be done in a librarical manner, which is creating a library is the partitioning itself. So first one, floor plan, right? Start GUI. GUI will be the graphical interface. Okay. See, this is the CPU we are going to design. These will be initially these will be not in this structure. As the first when we are creating library, it will be not in this structure. It will be very blank. It will be like blank. We should start designing our project. So I'll explain you what is in this. Everything is designed by our team or our past students. See, first step, we are going to design a this is a core, sorry, this is a die area, die, this is a core boundary, die. Wait, you can see a rectangle, one rectangle inside the other, right? So one inside the other rectangle, squares are actually, you take it as square. That was inner square was a core, and the outer was a die. We have some set of rules to maintain the space between die and core. Okay, using all specific rules and regulations, we are going to place a core and die first. So after that, our diagram will be looking like just two one in another. Our diagram will be showing like two one in another rectangles. After that, we are going to place our macros. These you can see, right? You can see these macros, right? These blockages. These all are called as macros. We gonna say storage elements, example like memory elements as a macros hereafter. When you are doing a project, we are going to place our macros uh, according to our project. As per our project having six macros to place. So some other projects may be having two macros, some other projects may be not even having a single macro also. So in our project, we'll be having a six macros to place, and that placement of macros should be done by our talent or our ideology or our own thinking perspective, which will need to be very easy when we do the further steps like placing our standard cells called gates over here, or when we are doing routing between the standard cells, should don't overlap or should don't create any mess or malfunctioning in our electronic device by misplacing the macros. Getting right? When we does a misplacement of macros or blocking the space will lead to our further steps very complicated. So in this manner, so everyone have a different perspective, right? Someone will place some macros the here and there, and even placing the macros will have also set of rules. Example, same like same functions or same specified macros should be in the same region, so that the working will be very easy. And macros should not block the input and output pins. These are input pins and these are output pins, which are also created by us using some commands. Okay, using some commands, we are these also created by us. And placing of macros should not interrupt any input and output pins. Afterwards, we should maintain enough space to place our standard cells. And these is the top view. Okay, you all know top view, right? Top view sites. You know, in the engineering graphics, when we have learned top view, front view, side view, and stuff. This is a top view. When you see this in a front view, it will be having a layers, 1 2 3 4 5. That in the same way, it will be having a 9 floors, 9 metal layers. It will be having, not actually a layers. We'll be having 9 metal layers to placement, routing, CTS, every separate things we will be doing in a one floor. Just assume we are constructing a huge apartment. Okay, let's take it as a 9 floor apartment. So we will be having set of rules in these things also when we are creating something, when we are placing the macros and all stuff. So let's move to the another block. See, after floor plan, we are going to do a power plan. Okay. After power plan, our chipset looks like this. So it's completely messy, right? Messy. We are going to do a power planning in the metal 9, metal 8, and metal 6. For your understanding purpose, in the very beginning, let's say like we are going to do our power planning in the 9th floor, 8th floor, and 6th floor in our constructed very early constructed building, very in the initial stage of construction of our apartment. We are going to do power plan, right? Giving every power supply to the every floor when we are leaving, or when we are having some stalls or shopping malls, if anything else, or any shops or complex or shops, we are going to give, even it is in a residential or shops also, we are going to give a power planning, right? So this is a power planning to the complete chipset. Let us eliminate, or let us make it visible or transparent to see what they are exactly. I'll show you clearly. See, these are the routings, power plan routings. We will do a power planning routings. These are routes. You can see here. These purple color one is a metal phi rail running all over the chipset. And this green one is a metal 4, and the red one you can't see, only few. Those are a metal 3. Getting, I have transparent, I have made transparent of metal 7, 9 and 8 and stuff all. Let me enable all. See, this orange one, metal 8, the biggest one, and metal 9, the white one. It will be more length, like thickness will be more when we are going to the higher metal layers. You can see, please keep an eye on this. Metal 3 is very thin and very small in size. When you go for the metal 4, in the green one, which is got wider, thicker, and metal 5 got a little more thicker, and metal 7 got a little more. So when we are going to the higher metal layers, the metal thickness will be going beyond. And power carrying conductors, whatever maybe they are, wires also in our daily life, wires also need to be very strong, right? Need to be very strong to hold our power, right? Getting, to hold our power perfectly, we are using a higher metal layers which are very thick in size. I can say you on a real time example. uh, you can see, you can observe, our household wires will be very thin in size, but high high level or high longest way current carrying metals, or wires like high tension wires, have you saw in the roadside, we will be having very power network, high tension wires called, they will be very thick in size, right? In the same way, when we are designing this, we'll be having a higher metal layers as a thick in size, just like a high tension wires. In the same way, we are also having a thick metal layers, same as a high tension. We'll have a thick layers at the higher metal layers, and you'll be giving some projects also. So next stage, we are going to do some placement. Fine. What is mean by placement? We have done a macro placement. We have given a core and die size estimations. We have placed some power plannings in the building. But we need to have a standard cells, right? Which are doing actual work, right? Standard cell does a actual logic function, right? Like gates are the one. Standard cells are these transistors or semiconductors itself do the actual work, right? So those are the placement stage. We are going to place every standard cell, each and every standard cells in a splitwise via splitwise. We'll be having set of rules to place a standard cells here. Let's see where are the standard cells. In this project, which we have took, we'll be having 60,000 standard cells. As per our project, 60,000 standard cells, which is operating in the 28 nanometer build technology. Got it. Let us turn off all these layers. When you are seeing this graphical interface, these are block after the placement. You are seeing something like amoeba shape, right? Here, just I'm kidding. These is the placement. These are the 60,000 standard cells placed in a core area, using all these macros, and we'll be placing some boundary cells. We'll be having rules when before we are going to place standard cells. We want to place like this tap cells, boundary cells, and everything to align the actual standard cells. Okay, same way. So these are the 60,000 standard cells placed in a core area. If we go more zoom into it, we can find the specific standard cell. See, this is the one standard cell. And this is the name of it. Right. Right, getting one block is a one standard cell. In the same way, we'll be having a 60,000 standard cells in here. We have just turned off our floor planning and stuff in the metal layers. If we turn on everything, the chipset actually look like this. See, till there we have done power planning, sorry, floor planning, macro placement, power planning, and placement. But we have didn't connected every standard cell, right? We have didn't connected any standard cell till now. We are just placed them, but we don't have any internal connections also, right? We have don't have any internal connections till now. So we are going to route. That process is called a routing. Before routing, we gonna do a CTS, clock tree synthesis. All right, clock tree synthesis. So what is mean by clock tree synthesis means, let me explain. Please be in a responsive state. You all know the natural processor or natural counters or a multiplexer, all will run on what? All will run on what? You know flip flops, right? A flip flop runs on a clock. Generally, you know the flip flops and latches. Everyone knows the flip flops, latches, all these things, multiplexes and everything. So we'll take a flip flops as an example. When a D flip flop will be very easy one, right? Sends the input to the output just when the clock edge arises. So when the D flip flop conducts, D flip flop conducts only when the clock edge, positive clock edge rises. Yeah, positive edge rises, the D flip flop conducts. So we have placed our standard cells, which may be a multiplexers in it, which may be an adders, whatever may be. We have placed the standard cells according to our RTL designers logic, which they have designed, right? According to that, using set of design rules and etc., we have placed everything. But we have supplied power also to you using a power planning, but we have still not placed any clock, right? Clocks. We have not placed any clock, so there will be no functioning. There will be no function. So you need to do a clock tree synthesis. Clock tree means, example, you know trees, right? Clock tree synthesis. The name itself shows what is there is a core, will be having a multiple cores, right? For example, when we'll discuss this later. Please remind me after explanation. We'll be having at least 5 minutes to discuss. Right. Okay. So we'll a clock tree. So assume clock as a branch, clock as a stem, actual stem of a tree, and leaves are the standard cells. So we are going to give the clock to the every leaves, right? The water which we are pouring to the tree will go to every leaf by branches, right? Branches and stuff. In the same way, we are using a clock. We'll partition it as a tree. Several branches will connect to the clock. After clock tree synthesis, so please see this diagram. This is a clock. This is another clocks, master, slave. The clocks will trigger to a standard cell like this. This is a clock tree synthesis. Clocks will be connected to every standard cell like this. Everyone understood, right, what is mean by CTS? And CTS also done in some another metal layer called metal layer 5. Placement, our standard cells will be placed in the lower level of the our core. Standard cells will be placed in a metal 1, 2, 3 maximum, And CTS and these things are internal routing will be done in 4, 5, 6 routing and CTS will be done. 6, 7, 8, and 9 metal layers, top end metal layers will done only power planning, and that power will be drawn to the bottommost layer to supply the power to every standard cell. Getting this is how the our chipset works. So after CTS, nothing will be changed much. These metal layers, right? You can't see some metal layers called 5, 6 in everywhere. You can see, but everywhere you can see. After CTS, it will be shown. So after that, we can see this is the diagram. This is our project after routing. Every metal layer will be used right now. Example, I'll stop showing I'll stop everything. I'll show you the metal layers which are used only for routing. Only one metal layer. I'll show you metal layer 6. All right. And there will be in middle you can see VR6 VRs. So VR cuts will be explained in the further classes if you in the course. It will be more in detail. I'll be giving a basic overview of everything. Is if we turn off everything, this is a metal 6 and metal 6 VR cuts. These are the metal 6, right? And see, you can see VR cuts, VRs. I'll say you a general definition of VRs. VRs are used to contact from one metal layer to another metal layer. Example, if you want to contact from metal layer 5 to 6, metal 5 will be the bridge. We have Wi-Fi will be acting as a bridge, conducting bridge. Okay, getting. This is the routing. After it will be having a timing enclosures, which are timing analysis will be done to our chipset, which we have designed. We'll see what is there any mistimings, timing violations, timing errors, lags. We'll be having a lot more in STA. So that will be checking and will close like timing enclosure will be done. That will be in a mathematical manner, not in a graphical manner or any commandical manner. Commands will be used if we want to fix it. We'll generate some timing reports and we'll sort it out. So these will be the actual thing we are going to do in our physical design. After this, our complete chipset and physical chip will be get ready, and that will be sent to a verification team, which they will be doing a verification, physical verification there, and that complete after verifications, the same project which we have done earlier, just now, will be sent to the fabrication department. They will be having a, right, TSMC. Have you heard about TSMC? Anyone? Taiwan manufacturing Taiwan Semiconductor Manufacturing Center. So, and such type of things, and in the future, we are also going to launch chip manufacturing center in our India, Gujarat itself. Adani groups are planning. India is the second semiconductor country in the world. So that team and that industry will manufacture and produce actual chipset which will be looking like this. Example, looking like this, packed, completely packed and sealed. Intel core chipset will be ready, and this will be connected to the motherboard, and users will be starting. So this is done by us as a VLSI engineers, and specifically we are specialized in physical designers and static timing analysis. So these will be learning, and these will be actually doing in a this thing industry oriented. In industry, these will be done, but I have just showed you an overview of everything, but in detail, it will takes lots of time. If you want to design a one chipset, if it is a newer one, taking all R&D and research and development, everything, a chip manufacturer or a complete chip design will takes approximately 1 year of time, working 5 to 10 teams, approximately 1,000 people working continuously for 1 year will develop only one chipset. If it is a flagship chipset like i5, i7, i9, some we also having some basic chipsets right in TVs and stuff. Yeah, okay. Yeah, you can say Snapdragon 888 or 8 plus Gen 1. Generally, now in now present situation, we are using Qualcomm Snapdragon 8 plus Gen 3, and which was built on 4 nanometer build technology, which was very fast in it. Right, you can see the legal data sheets. You can find somewhat information, benchmark scores, and etc. When you are buying some mobile phones, you'll be seeing like Qualcomm Snapdragon 675 octa-core processor, and Apple A16 binary chipset only has a hexa-core processor. They only manufactures hexa-core like 1, 2, 3, 4, 5, and 6. There will be only 6 cores. 6 cores. Like yeah, everyone says octa-core nowadays. Everyone uses octa-core. Even MediaTek and Qualcomm, everyone uses only octa-core. Only Apple uses the hexa-core thing. Okay, octa-core. See, let's see this. 1, 2, 3, 4, 5, 6, 7, 8. It will be having 8 segments. Maybe they are somewhat confused. Let me show you the actual diagrams. You will get you will get false informations from the internet if you search for electronics and VLSI code. Everyone will only produce their own bloggings, their own thought. So you need to have a IEEE papers or IEEE access so that you can find a real information. See, this is the quad core, 4 cores inside. This is octa core. 8 cores will be inside a one chipset, complete chipset, and that cores are different. That course will be managed in different sectors. Like, see here, if we see this Apple A16 Bionic chipset, we'll be having one core as a CPU, one core as a GPU, and sorry, 6 core CPU, which will be having. Let me explain in more detail. It's a complete chipset, like a full chipset. In that, we are designing 6 core CPU. In this 6 core, right? 1, 2, 3, 4, 5, 6. You found 6 cores, right? 6 cores. So we will develop a will develop a core based on our technology. Have you heard about ARM cores, ARM cores? Yeah, ARM cores. If we are using a octa-core processor, if we takes someone said right, Snapdragon 888, 8 plus Gen 1, 8 plus Gen 2. So every core and every chipset will having a testing circuit designed, testing circuit placed by the time of designing only to test it or verify it after designing, after the actual product released. Okay, you need to develop some. We'll be having some another softwares to testing or verification purpose. Same in the mental graphics, same in the cadence, and same in the synopsis. We'll be having some other top softwares like same as ICC2. Verification will be having some other tools which will be thought that also will be and another department it will be. Right, and someone asked what is difference between CPU and GPU. See, CPU is a central processing unit which will be more responsible on our processing. So CPU will be more responsible or more taking responsibility on doing some processing some application. Example, see, we are opening this Google Meet application, right? We are using some Google Meet application. Central processing unit does a process of opening that application and processing that application to run everything. in the backend side, run everything. Like when I'm talking, that should be audible to everyone in this meeting. The process of joining you guys into this meeting, the process of me as a host in this, the process of someone will be the co-host. These are the process, right? Everything process. So that will be done by a CPU. And GPU is a graphical core that will be more bothered on graphics. Example, when I am opening these same Google Meet, we'll have some graphics, right? For example, I'm stopping this presentation right now. See, you can find some graphics.